So far in this course, we have looked at a number of ways of solving planning problems efficiently. That is, we have assumed that we were given a planning problem. But a planning problem is a very specific artifact, and to get to this artifact requires a lot of work. So we have a lot of problems we need to solve before we can start planning, and that's what we will look at now briefly. The first problem that we need to solve before we can do any planning is the knowledge engineering problem. One thing we have learned on this course is what the planner takes as input, namely a planning problem consisting of an initial state, a goal, and a set of operators that we can use to move through the state space. And for a planner to use this as input, all this needs to be represented in a formal language, such as PDDL. Knowledge engineering is really everything that we need to do to get from the first informal problem description to this formal representation that we can give to a planner. And this involves the problem of problem formulation that I've already talked about when I've introduced you to the missionaries and cannibals problem. And problem formulation is really vital for the efficiency with which we can do problem solving. If the operators we choose to represent contain too much detail, then the state space can explode exponentially and we cannot solve problems anymore. But that is only one of the concerns during knowledge engineering. There are others, like how adequate is the knowledge we have represented, or how easy will it be to maintain in the future. There are now tools that we can use to perform the knowledge engineering for planning domains. And these tools support one or more phases of knowledge representation as shown here. The first phase that we need to go through is the requirement specification. This is where we talk to domain experts and try to find out what they expect from the system that we will build as a result of this process. Then the second phase is knowledge modeling, where we take the knowledge that we've extracted from the experts in the first phase and build a formal model, but a formal model that the experts can still understand and critique, so it needs to be fairly high level. Then we can do a model analysis, which involves verification and validation, finding out whether the model is adequate and captures all the knowledge that we need. Then we can deploy the model, which means we have to export our domain specification in a language and formalism that a planner can understand. This is then followed by plan synthesis, which is essentially what we've looked at in this course. And finally, we can do plan analysis and post-design, which is we look at the generated plans, go back to the experts and show them, is this really what you wanted? Are these plans useful to you? What criteria do we have to assess these plans? And overall, this is an iterative process, so that means we can go back to any phase at any time and start over again to improve the model. As you can see, knowledge engineering for planning domains is anything but trivial. But there is an alternative approach to doing all this manually, and that is to try to learn planning domain models. The basic idea here is that you build a system that can observe what is going on in a specific domain and derive operator descriptions that describe how the state of the world changes as the system sees it. This has been done recently for the game of FreeCell, where a system observed the game playing for a while and then came up with a formal definition of operators that describe how to play this game. One of the problems that keeps coming up during knowledge engineering for reasoning about actions and change is the frame problem. And to explain this to you, I need to go back in time a little. Back when people were first looking at planning problems in the 60s, a very popular field in AI and in which a lot of progress was being made was automated theorem proving. So one of the earliest approaches to solving planning problems then was to transform a planning problem into a theorem proving problem. And doing that involves writing a set of logical axioms that represent what changes in the world when an action happens. There were, of course, axioms expressing the preconditions of an operator, and there were axioms expressing the effects of an operator. But it turned out, for a theorem prover to work, you also needed to write down explicitly what doesn't change when an action is executed. And in fact, the list of things that don't change when an action is executed is much longer than the list of things that do change. So the problem was that we needed to represent a long list of facts that are not changed by an action. And the frame problem in general then is to construct a formal framework for the reasoning about actions and change in which the non-effects of actions do not have to be enumerated explicitly. The formal framework that was used originally was first-order logic and using theorem proving as a problem-solving technique. And the specific set of relations and functions that were used to represent operators in first-order logic are known as the situation calculus. Now, there are a number of ways in which the frame problem can be approached. And the first one was to ask the question whether we can use a different style of representation. So we don't use the situation calculus, but we use a different way of encoding the same knowledge in first-order logic. So we keep the formalism. And while there has been some progress with this approach, the problem of enumerating non-effects of actions explicitly did remain in some way or other. The second approach then was to use a different logical formalism. So instead of first-order logic, we may be able to use a more complicated formalism that can encode the knowledge better. And one good candidate was always non-monotonic logic. And again, there has been some progress in that area. But theorem provers for non-monotonic logic are not very efficient. And the third approach was to simply write a procedure that generates the right conclusions, in our case plans, because its solution is built into the procedure. And that third approach is basically what we've been following on this course. But you should be aware of the frame problem, which has to do with the representation of non-effects of actions.